Owl wings have received a lot of attention from aerodynamicists over the years because they are a little different to most other bird wings. One major difference is that owl wings are known for being very quiet, which makes them very effective as predators. Why do their wings produce so little noise, and is their aerodynamic performance compromised because of it? And is an owl wing better than a regular airfoil of the same general dimensions? That is what we're looking at today. And to answer these questions, we're looking at a paper called A Numerical Study of Aerodynamic Performance and Noise of a Bionic Airfoil Based on Owl Wing. So this paper right here. And this paper is open access, so you can find it in the link below. And this study is pretty cool because if you've listened to some of our other podcasts, you know that we often talk about just how difficult it is to accurately simulate noise produced off of something. And in fact, probably the first time I came across this was like my first year of my PhD. I remember like literally it was maybe the first or second week. And I was talking with one of my friends who was a more senior PhD at the time. He was like third year by then. He was telling me about his research more in depth, and he was looking at the noise production of a submarine's hydrofoil, or the different hydrofoils around a submarine. And this was quite a long time ago, back when RANS and URANS was the standard approach, and he was having so much trouble getting accurate results. That was mostly because of the turbulence model used, and the reason why the turbulence model is so important is because noise really comes from turbulence and fluctuations in pressure. Now, any CFD that uses a turbulence model then relies on a kind of stochastic approach, which means that you're not accurately capturing the turbulence properly, but just approximating it. That approximation results in all of the finer details being lost, and those details are often very important for noise. So since that time, the Aeroacoustics field has advanced to DES and then again advanced to LES. And that is what we're looking at this paper here. These authors used LES to simulate the aerodynamics and aeroacoustics of an owl wing, and then compared it also to a NACA wing of similar dimensions to find out if the noise produced as well as the general performance has changed. So with the LES approach, which stands for large eddy simulation, this is much more accurate than RANS or URANS because it actually solves for the larger turbulent structures, and comparing that to RANS and URANS, that is really good because those other approaches don't even resolve the larger structures. Now, LES still isn't perfect though, because it doesn't resolve the smaller scale stuff. As the name suggests, the name is large eddy simulation. That tells us that they are clearly only resolving the large stuff here. And that is really good, at least compared to what has been done in the past. But the assumption is that the larger turbulent structures, such as the large vortices, contain most of the energy in the flow. As such, these larger structures dominate the aerodynamics and the evolution of the flow. This theory is backed up by the von Karman scale, which shows that indeed the larger turbulent structures contain more of the energy as you go, and as you go to smaller and smaller structures, you get less and less energy in these little structures. And now the assumption then becomes that if a structure has less energy, it plays a less important role in the flow than a structure with a lot of energy. Hence why LES, generally speaking, is going to be more accurate than URANS and RANS, because even though we're not capturing the small scale stuff, the larger scale stuff is more important for the flow. So overall, that assumption is definitely true, but it is not always true. So one example of when it is true is consider a laminar boundary layer. And when you have a strong vortex right next to it, well, that vortex is going to greatly affect the boundary layer and probably even cause it to transition to turbulent. Contrasting that to if the vortex were weaker, well, it will still affect the boundary layer, but it won't cause it to transition to turbulence. Now, right there, we can see how a structure with a lot of energy will affect the flow more than a structure with a little amount of energy. However, that doesn't always mean that the structures with a lot of energy in the flow will always affect the flow more than the structures with little energy. So one example where a structure with less energy is more important than a structure with more energy is, for example, let's say we revisit the idea of a laminar boundary layer. So let's now say we have a structure with a lot of energy, but it is nowhere near the boundary layer, it's somewhere else. And let's say it's floating off into space and it's not going to be affecting the boundary layer. Alternatively, if we have a structure with little energy, but it is located in the boundary layer, then it will affect the flow more than that high energy structure that was nowhere near the boundary layer. So in this case, we have seen that a structure with a little amount of energy affects the flow a lot more than a structure with a lot of amount of energy based on where it is. So bringing this all back to LES, The overall assumption when using LES is that the structures with a lot of energy affect the flow more than the structures with little energy. And on average, that is definitely true. But we can see now how under some circumstances that isn't true. So yes, LES is definitely a step up from RANS, URANS, and even DES, which is a combination of URANS and LES, but LES is still not perfect. Now, during that explanation of what LES is and its strengths and weaknesses, I didn't mention what we do when it comes to modeling the small scale stuff. So we know that in LES, we do resolve the large scale stuff, but the small scale stuff we can still affect the flow. So what do we do about that? Well, there are two common ways of modeling the small scale stuff, and that is something called the Smagolinsky or the Wall, or WALE, Waller, subgrid scale models. And you can think of them as akin to like the turbulence models used in RANS. So in RANS, you have like maybe K omega, K epsilon, SST, KKL, omega, and so on. These are all different turbulence models, and each is designed to work well under different conditions. At least, ideally, they're designed to work well. Sometimes they don't work that well. But anyway, so the Smagolinsky and Wall models are the same kind of thing, just for LES. They are different options to help us model the small scale stuff based on what is happening in the flow around this region. And for this paper, these authors, as we will see, are using LES to simulate the flow around the owl wing, and then also consider different subgrid scales. So at this point, I should also say that what we went through here is just the start of all this. And if you want to learn more about LES and RANS and all these different turbulence models and subgrid scales, we covered in our CFD course, a few of them, for example, the intermediate course, which you can find below. So if you want to pick up from where we left off here in this CFD talk about LES and Smagolinsky scales, etc., then the intermediate CFD course that we have is right for you. But let's get back to this paper. So one of the major reasons why understanding owl wings, and in particular how they reduce noise, is because we can then make our inventions and machines much quieter. There are many examples of how noise really limits the usability of a machine, and one of the most impactful ones, to me at least, is flying cars. So I actually have some friends who have a company making flying cars, and one of the most restrictive problems they have when making these flying cars is making them quiet enough so they can be used in urban environments. So using flow control devices that nature has already perfected over millions of years of evolution is a very attractive idea. And when it comes to owls, they are very stealthy, as this paper will demonstrate. So one thing I should mention about sound is that when you get a 3 decibel reduction in the noise, that isn't a little reduction, that is a huge reduction. That means that you've halved the noise, 50%. So even going from like 110 decibels to 107 decibels, it doesn't seem much. It's just 3 decibels, especially over like a 110 decibel range. But believe it or not, that 3 decibel reduction is a 50% reduction in loudness. So anyway, for this paper, these researchers used the Fluent CFD package, which is the most common CFD software. And for the airfoil model, the researchers said that they selected the owl wing because its geometrical features were preferable at low Reynolds numbers and could suppress sound generation by unsteady pressure pulsations on the wing's surface. So that's cool. What they are saying is that the wing itself creates pressure fluctuations, which then reduces the noise. So in figure 1, we see the owl's wings profile. It is very similar to the early days in flight, actually. For example, the Wright brothers flyer, where the wings were very thin and the maximum thickness occurred very close to the leading edge. In this particular case, the maximum thickness is only 5% of the chord, like from the leading edge. Sorry, it's only 5% thickness of the chord and occurs 10% from the leading edge. So it's like really bunched up very closely to the leading edge. And then as you go all the way down the wing, it becomes very slender and it's almost like an eyebrow hair. Like if you were to zoom it in, how you have the root is like really thick and then the rest of the hair is like thin. That's kind of what it looks like, I guess. Comparing that to many typical airfoils these days, it is very close to the leading edge's thickness. Many airfoils these days have the maximum thickness more around the 25% from the leading edge mark instead of like 5 or 10%. So now the important thing to keep in mind is that owl wings, like every bird's wings, are multi-purpose. They are not only used for gliding flight, but also for flapping. That is an important distinction to make because just because a wing might be good during one phase of flight, like gliding, doesn't necessarily mean that it will be good when flapping. And in fact, flapping flight is very complicated. We've actually done quite a few podcasts on that topic. And owl wings are like the wings that are best compromised between the different phases of flight for this bird. So they say that the free stream Mach number is 7.5, the free stream velocity is 7.5 meters per second, which gave a Reynolds number of 12,300. That is really low, and we'll see a quite surprising flow feature later on, despite being at such a low Reynolds number. So at this Reynolds number, the flow will almost certainly be laminar, which makes CFDing it significantly easier. In fact, it means that the number of cells you need to use and the resolution for the LES can be lower. So in figure 2, we see their domain, and they have the C-shaped inlet, which is a clever way of reducing how many times you need to mesh your setup. So the reason why it is a really clever way and it reduces the amount of times you have to mesh your setup is if you wanted to test different angles of attack, all you need to do is change the inlet flow angle. So for example, instead of coming straight on, it's coming in at an angle this way. And then you run the simulations again. And comparing this to if you had to like have a rectangular front, so just a square front, you'd have to change the pitch angle of the airfoil, like the CAD, then remesh the entire thing, and then run everything again. So by having this C inlet shape, you get rid of that changing of the CAD and then the remeshing, so you really save a lot of time. Now, this is the second week in a row where, at least to me, the distance in the inlet is either much too close or the distance to the outlet is too little. The reason I say that is because this airfoil is located 30 chords downstream of the inlet and 30 chords upstream of the outlet. To me, I think that distance from the outlet is good, 30 chords. That's enough time for the wake to develop. But I think the distance to the inlet is too much because yes, you have upstream effects, considering that we have such a low Mach number and this airfoil is so sleek, the effects are nowhere near as great as the wake you get from the wing. So on the other hand, behind the wing, you certainly have a distance for the wake to evolve. And in comparison, that is going to require a lot more distance to occur than the upstream effects occurring of the wing. So all of this, I think, means that the inlet is probably a little bit further away from the airfoil than what it needs to be. And that isn't bad for accuracy, but in terms of efficiency, it just means that your CFD is less efficient because you need to use more cells than what you really would have to. So I would be inclined to move this inlet a little bit closer to the leading edge of the wing. As far as I can see, there was no sensitivity study on the effect of this inlet distance to the wing on the parameters that they're interested in. So I think it is simply too far away and costing you more cells. Anyway, these authors did do a grid independent study, which is great, and we can see that in figure 3. And the parameter that they were interested in was the lift to drag ratio. So this parameter is the most common way of measuring the efficiency of a wing, where the higher this value is, the more efficient the wing is. So in this figure 3, we see the effects of the number of cells on the x-axis, the effects of that on the lift to drag ratio on the y-axis. Now, this simulation isn't two-dimensional, but it isn't three-dimensional either. It's what you would call like 2.5 dimensional. So this is a little bit funny. It's a bit strange to say it this way. So let me explain what this means. So 2D is simply where you have your CFD solving in 2 dimensions only. So you have the x and y velocities. 3D is where you have the third dimension, and you have so obviously the z velocity as well. But the term is 2.5 dimensions, where I've used this CFD is solving in 3 dimensions, but you don't have the complete geometry. You only have a thin slice of the geometry, and then you have the periodic boundary conditions applied on the left and right faces to replicate having the entire geometry. So that is called a 2.5D simulation. So to give you an idea of how this could change the flow physics, imagine a 3D wing. You get a wingtip vortex that affects much of the span. If you have a 2.5D simulation, you don't get that wingtip vortex because you aren't modeling that section of the wing. You just have some sliver in the middle. But you can still get 3D flow physics that arises over that sliver of the wing when you're modeling it. So the simulation is more than 2D because you have the third direction, so the z component of the velocity, but it's not really 3D because you don't have the entire full geometry or the effects from the regions outside the periodic boundary conditions. So in this particular simulation, the researchers, as shown in figure 4, only had a sliver of the wing, and that sliver had a span of 0.2 times the chord. And then on the left and right faces, they applied periodic boundary conditions. So this is an important point because it can change the flow physics. And also that helps us understand figure 3 a little more, because if you see how many cells they used, they only considered up to 1.8 million cells, which if you were to use RANs or URANs, that would be a decent amount for the entire wing. That's really sweet. But for LES, 1.5 million isn't very much, and you'd probably need more, around 5 or 10 times that many cells to get a proper CFD simulation of an out wing, even though it's such a small wing, but that's just how demanding LES is. Anyway, for the grid independent study, we can see that the lift to drag ratio has definitely started to plateau as we get to higher numbers of cells used, but that only really starts to occur at about 1.5 million cells. In other words, going from 1.2 million cells to 1.5 million cells, the lift to drag ratio still is changing quite a lot. But once they went from 1.5 million cells to 1.8 million cells, the lift to drag ratio was bang on now. Like, it didn't really change much at all. But that increase from 1.5 million to 1.8 million cells is still too low to conclude, for an LES simulation at least, that the grid has converged. In reality, they should have gone to a much higher number of cells, like 2.5 million or higher, to see how that converged. So the grid convergence study shows that as the number of cells increases, the lift to drag ratio does converge, but it's not definitely true. We can't tell right now if the number of cells you need to use was 1.5 million or higher. Now, in figure 5, we see the Y plus values over the surface of the owl. And I must say they did a really good job here. It's excellent, like the results that they have. The Y plus values are well below 1, and most of the time like really well below 1, like 0.2 or less. So they are capturing all the important details at least as far as the Y plus theory goes. And if you don't know what the Y plus value represents, it is really just how well you're resolving what is going on in the boundary layer, and particularly very close to the wall, which is where much of a boundary layer's flow physics originates from. So you definitely want to capture this region if you're doing LES. Now, they talk about the time step that they used down here. And this is literally just the amount of time each iteration marches forward. And this is a very important parameter for all of the unsteady CFD cases. And here they say that they needed to ensure the accuracy of the calculation by having a small enough time step, which is completely true. They then say that for this reason, they use a time step of 1 by 10 to the negative 5, which is 50 microseconds. Now, I don't really know if that is a small enough time step for this simulation, because I can't see a time step independent study where they looked at the effects of different time steps on the simulation results. In fact, the reason they give for choosing this time step is that this value, at this value, a particle of air traveling at the free stream velocity of 7.5 meters per second would take 10,000 time steps to travel over the entire wing from the leading edge to the trailing edge. While that is an interesting fact, I don't know how that relates to the flow physics. I mean, if there is some general equation that links this value to sound generation that I'm not aware of, then they haven't got that here either. So I'm not really sure if this time step is adequate or not. It would be nice to know if they considered the time step in their like a time step independent study, but we don't have that information here, so it's a little bit difficult to conclude if this time step is adequate or not. So in fact, actually, I would have really liked to have seen the Courant number, because this tells us how many cells a hypothetical bit of air will travel through in a time step. This value is much more useful than what is currently given, because we have metrics that tell us if the Courant number is good or not, and that's really applicable for such a wide range of simulation cases. So just as a side note, if the Courant number is below 1, then you've got a really good time step. If it is below 5, then that's generally acceptable. And if it is above that, then the time step needs to be reduced. So finally, I should mention that their CFD here doesn't seem to incorporate any validation data, at least from what I can see. So as such, I can't tell how accurate this simulation is. So overall, there are some really good points about this CFD setup. For example, the LES and the fact that they're using LES and the Y plus values, they're all great. But there are some bad points. For example, no validation, and the grid independent study is a little off. And also, I can't tell if this time step is good or not, which means that it may or may not be good, but I simply cannot tell. So overall, I think this CFD is like a 6 out of 10. I think that we can use it to see the flow physics in general, but when it comes to the exact numbers, we should take the results only as a general guide and not necessarily as completely right. However, let's now move on to the results, because first we have a very surprising finding. So remember back in this podcast, I was talking briefly about separation bubbles. I accidentally mentioned it. So let me explain what these are here. So A separation bubble, that is simply where the flow separates over the surface and then reattaches at some point downstream. This then creates a bubble of recirculating air that is separate from the rest of the flow. So separation bubbles aren't that surprising. I mean, many things have them, but the surprising thing is that they are occurring on this wing because the Reynolds number is so low. So we see here in figure 6 here, these top few, we see some separation bubbles forming, and usually that they should be forming at a much higher Reynolds number. General literature says that the lower limit for a separation bubble to form is at a Reynolds number of about 50,000. And there is a pretty good reason for that. It is largely to do with the fact that separation bubbles do trigger transition to turbulence. So having a bubble forming here at a Reynolds number of only 12,300 is pretty amazing. Imagine having a turbulent flow at such a low Reynolds number, because that's what will be happening. And you can do that, but it takes a lot of boundary layer tripping and surface roughness and so on. So to get it here quite naturally is very surprising. Also, another really interesting point is that for some of these figures, we see that these bubbles forming on the pressure side, so underneath here, which is very strange. Usually they only form just on the top, but for example, on figure 6a, we can see the streamlines circulating around underneath and being very compact here, which is the bubble. And then on top near the trailing edge, which is another bubble here, and we also get that here and here. So I should note that these figures, figure 6a and figure 6b, they are just for very low angles of attack, just 0 degrees and 1.5 degrees. As it pitches higher, the bubbles disappear very quickly. I mean, at 3 degrees, the underside bubble is completely gone, and at 4.5 degrees, the upper side bubble is now gone too. Now, one more thing that is very interesting is that pitching the airfoil to only 7.5 degrees, so this lower figure here, 6F, results in a massive flow separation, and it is very sudden. I mean, going from 6 degrees to 7.5 degrees is just a 1.5 degree change, and that results in a sudden flow separation of over like 90% of the airfoil. It goes from like 40% of the airfoil separated to now 90% of the airfoil separated. So in fact, in figure 7b, we see a plot showing how much of the owl's wings is exposed to separated flow with angle of attack. The x-axis is the distance from the leading edge, with the 0 being the leading edge and 1 being the trailing edge, and the y-axis is the angle of attack. So as angle of attack increases, we have more and more of the flow separated over the airfoil. So that tells us a few things. The first thing is that owls typically don't glide at very high angles of attack, because if they did, as you can see from this plot, as you increase the angle of attack a little bit more, we get more and more flow separation, and it's very rapid. In fact, I would say that owls don't even get close to gliding at 7.5 degrees, because even just a slight change in angle of attack would result in a significant amount of more flow separation and become potentially unstable. So I think that we can conclude that owls glide at low angles of attack, and high five to them, because that's what we do with our planes, so we're all cool kids. So now, the next thing we can conclude is that owl wings are really only effective at high angle of attack if they are flapping. And in fact, owls rely on the dynamic motion and the resulting vortices being shed to produce lift at these high angles of attack. It's really quite amazing, because it's like nature and evolution has made these wings so perfect for animal flight. So let me explain what I mean. So the owl wing is very thin. It is quite similar to a NACA 0006, and the bird flaps its wings to produce a lot of lift. Well, at low angles of attack, a thin wing, like the owl wing, is far more efficient for gliding than a thick wing. To give you an idea, for this Reynolds number range, the literature says that for a NACA 0006 airfoil, so a very thin one, it has a maximum lift to drag ratio of 15, while a NACA 0024 airfoil, which is really thick, it's a big boy, that only has a lift to drag ratio of about 8, so half that of a NACA 0006. So simply through evolution, the owl wing has gotten so thin because that is more efficient for gliding and still good while producing higher lift, because the owl can then flap its wings. So now in figure 8, we see the lift coefficient plot, and it is very non-linear, which is very much due to the separation bubbles on the lower and upper surfaces. The reason why these bubbles affect the lift curve so much is because each bubble effectively acts like additional thickness to the wing. A thicker wing means more or less camber and lift. So at 0 degrees and 1.5 degrees, the lift curve slope is quite low, and then at 3 degrees, it suddenly shoots up. That is because just before this angle of attack, the bubble on the underside popped. So down here, the bubble is still intact, then it popped. That results in effectively the upper side having a thicker surface, like it's more cambered now, this airfoil, and hence it produces more lift. One other thing that is very interesting about this figure is that even at 0 degrees, the wing is producing a decent amount of lift, and the lift coefficient is about 0.35, which I think would be more than enough for the owl to glide down. Now in figure 9, we see the drag coefficient, and it's not that surprising here. It's just a typical drag bucket. One exception might be that the drag coefficient at 0 degrees is about 15% higher than at 1.5 degrees, but that might just be due to CFD error. So I'm not too sure about that. Other than that, this drag coefficient plot is quite expected. Now, in figure 10, we see the lift to drag ratios of not only the owl wing, but also the NACA 0006 wing that they tested in CFD. And this is the first comparison we're getting between these two airfoils. So the results are very interesting. Remember how I said a few minutes ago that the NACA 0006 airfoil is already really good at angles of attack? Well, the owl wing trounces it as well. So, I mean, across the entire range of angles of attack here, the owl wing has a much better lift to drag ratio. For example, at 0 degrees, the NACA 0006 airfoil has a lift to drag ratio of about 0, while the owl wing is at 7.5. At 6 degrees, the NACA 0006 airfoil has a lift to drag ratio of about 8, while the owl wing is at about 15. Also, the owl wing's lift to drag ratio is much more stable across the angle attack range than the NACA 0006 airfoil. The NACA 006 airfoil rises, peaks, and falls much more sharply than the owl wing, whereas the owl wing lift to drag ratio is a lot more flat. So that is the aerodynamics of this wing. Let's move on to the acoustics now, because we see some really cool stuff. So in figure 12, we have the loudness of the wing as observed at different points around the wing. So we have the wing here, and then we have different points all the way around. Now, there are two things that are really interesting here. The first is the scale. So the scale only goes up to 30 decibels, as you can see here. And in fact, that sound only ever gets up to about 28 decibels anywhere. So the scale is 30, and this owl is only really producing at most 28 decibels from its wing. That is quiet. That is quieter than anywhere pretty much in your house. That is quieter than a forest, really. I mean, literally, when I went home, I downloaded a sound meter app on my phone and then measured the noise level in my bedroom at night. It was like 33 decibels. This wing is 28 decibels. And remember how I said that a 3 decibel reduction is about half the power? Well, a 5 decibel reduction is like 65% reduction. So the noise owls make when gliding from their wings is 65% less than the noise in my bedroom when sleeping. And maybe I should just sleep around owls flying around instead. In fact, I looked it up, and 28 decibels is about the noise produced by slightly asthmatic wheezing. So if your wife, husband, girlfriend, boyfriend is slightly asthmatic, lying next to you, she or he is about as loud as an owl gliding. And I need to stress that the level here is just when you're below or above the owl. If you are in front or behind the owl, the noise drops to 5 decibels. 5. That's nothing. In fact, we have the frequency spectrum, and by far, the noise in figure 13, by far the noise coming from the owl while gliding is mostly in the low frequency range, predominantly below 2000 Hertz. So to give you an idea of this frequency range, what I've been saying around now, my voice is around about 1000 Hertz. So that is about the tone you would hear from an owl gliding along, if you can hear it, that is. In addition to that, figure 14 shows where the sound is coming from. And by far, the most sound is coming from the trailing edge and the rear part of the airfoil. And if you were to put serrated feathers onto the trailing edge here, which owls often do have, that noise would drop and the airfoil would drop way down below 28 decibels. You probably wouldn't be able to hear it at all. And with that revelation, we come to the end of this podcast. If you liked it, make sure to hit the like button and click the subscribe or follow button, whichever platform you're on. And if you want to learn how to do OpenFOAM, take our course in the link below. OpenFOAM is a great and free CFD software, but it is really hard to learn. Our courses takes you step by step through how to use it, and even literally from installing it. So we have other CFD courses as well you can take in the links below. And we saw in this paper that there were no experiments done. But if you were doing experiments, then you should know that there is probably a 2 to 4% error in your data, simply because the density of air in your wind tunnel is constantly changing. To account for that change and mitigate that error, we made the Atmosphere Hawk, which has very accurate instrumentation to measure the density of air for you. You can find that in the link below and get one to improve your experiments, get more accurate data, find more trends, and publish more and better papers. You can also find the link to the math breaking down how the density changes and why below. So that is in this podcast. It was a cool one, and catch you in the next one. Peace out, amigos.